A further example of conjugate priors. Let's take a system where we have a Poisson process governing the number of faults in a given time, but that the rate of these faults occurring is not known. What that means is a little bit of revision of some distributions. The times between successive events in the Poisson process are realizations of an exponential variable with some rate parameter, which is positive. Let's say we start by saying we believe that the rate parameter here is something that can be described by a gamma distribution with parameters 1 and 2. So what that says is I think the rate at which faults arrive in that system is about half a fault per unit of time, so 1 fault every 2 units of time, but that I can update that as I get more and more observations. So this is a gamma with parameters 1 and 2. Some textbooks might give you a slightly different parameterization for the gamma, but I'll keep this consistent with one of the 2 standard notations. So let's say we actually observe the times between the arrival of these faults. So I say, I think on average there's half a fault per unit of time. So 1 fault every 2 units. So let me wait until I see a fault and note down how long I waited. Then let me wait until I see another fault and note how much longer I waited for that. And if I do that, I can write down the likelihood of, if I knew the rate parameter lambda, which I don't, but if I knew that, the likelihood that the waiting time for the first fault was W1, the waiting time for the second fault was W2, after that, and so on. And because these are all realizations of an exponential random variable, this lambda e to the minus lambda times the waiting time is the form for the likelihood. Now I can of course simplify lambda times lambda times lambda n times over to be lambda to the n. And similarly, multiplying the exponentials, I add the exponents. So now when I get to Bayes' theorem, then I've got the likelihood times the prior, and then I suppose integrated out over the uncertainties and that, but let's ignore the denominator for now and just work on the numerator, the proportional to the prior times the likelihood. When we calculate the numerator, the likelihood times the prior, we've already worked out that the likelihood is this lambda to the n e to the minus lambda times the sum of the waiting times. The prior distribution we've said we will define as a gamma distribution. But what I can see here is this beta to the alpha, that's just a constant, the gamma alpha is just a constant. So the parts which are not just constant with respect to lambda, well, my prior has a lambda to the alpha minus 1 e to the minus beta lambda. So it has, again, a lambda to the sum power and an e to the minus something times lambda. So what this does mean is that I can really tidily and nicely combine the information from my prior with the information from my likelihood. And when I do that, of course, instead of just having lambda to the n and lambda to the alpha minus 1 multiplied together, I get lambda to the n plus alpha minus 1. And instead of having e to the minus lambda times the sum of my waiting times and e to the minus beta lambda, I get e to the minus lambda times beta plus the sum of my waiting times. If I put all of this together, I can then just, I suppose, reverse the whole process and go into pattern matching and say, oh, well, a beta distribution has my variable to some parameter minus 1, e to the minus my variable times another parameter. And so matching that up, I end with a gamma distribution, except instead of my parameters being alpha and beta, they're n plus alpha, and the sum of these waiting times plus beta, the waiting times for the next fault in this scenario. And what that means is if I start by saying there is half a fault per hour, so an average or per unit of time, if I start by saying there's an average of 2 units of time between faults, I believe, but then my first fault happens after half a unit of time, my next fault happens after 0.3 after that, my next 1.3 after that, my next 1.2 after that. That doesn't look to me like they're happening at a rate of half a fault per unit of time. That looks to be happening a lot higher rate. So if I put that evidence and blend it with my prior belief, I'll end up with a gamma where instead of alpha being 1, it's n equals 4 plus 1. And instead of it being beta equals 2, it's beta plus 0.5 plus 0.3 plus 0.3 plus 0.2 is 3.3. So in other words, my posterior belief, it's really pulled my belief up in the scale. It's yanked it away from that tightly being packed around a half. The middle of that distribution is further to the right, and it's got a much longer tail, which is what I expect. That my new evidence didn't confirm my prior, quite the opposite. It made me reconsider what I should think for my posterior. And just one other example, a negative binomial, which we can think of as a sum of independent geometrics. So instead of saying, how many times do I flip this coin until it first lands heads, this might be, how many times do I flip the coin until I've seen heads 10 times. So in this case, well, r times. So obviously the rth success can be on the rth attempt, or the r plus 1th, or the r plus 2th, and so on. So this is the probability mass function for this. And it depends if I know r, but I don't know p, depends on this parameter p. How likely is a success on a given trial? Let's say I've got a whole sequence of observations of this. I can write down the likelihood of these. But I still want to put some prior belief on what P is, what the chance of success on any given trial is. So because it's a probability, I'll use a beta because that constrains it to be between 0 and 1. So I'll define a beta with parameters A and B for my prior. We saw previously what the density function of a beta is. I want to show that this is a conjugate prior. The way I would show that this is a conjugate prior is by writing down the posterior. And the posterior is the product of the prior times the likelihood, or well, proportional to the product of the prior and the likelihood. The prior we set as a beta distribution, so is proportional to p to the alpha minus 1, 1 minus p to the beta minus 1, and the likelihood of these negative binomial samples, well, it's a little bit ugly at the front, but the part which actually has the p involved, the parameter I'm interested in involved, is just a product of p to the r times 1 minus p to the ni minus r multiplied over however many observations I have. So what it does mean is that I can start to then unpack what that product term looks like. So I've definitely got p to the alpha minus 1, then I've got p to the r in each of those terms. So in fact, I'm just summing r plus r plus r m times over. That part's quite easy. I've then got this 1 minus p to the beta minus 1, but then I've got this 1 minus p to the sum of these ni minus r terms. If I just tidy that up a little bit, well, r added to itself m times over will just give me mr, so I'll get a p to the alpha plus mr minus 1, and similarly at the back end, I can combine the 1 minus p powers as well. If I do that, all I'm left with is adding mr to the first parameter and adding the sum of the ni's minus mr to the back parameter. And what this means is that by starting with a beta prior, I end with a beta posterior. So I've shown that the beta is a conjugate prior, not only for single Bernoulli trials, but also for larger, more complicated negative binomial datasets.